Alrighty then. Well, the thing is going red. That must mean we're live. Why? Isn't that the universal sign that we're being recorded? Shh. Hey guys, what's going on? Memes here. And we're back. And we're continuing on our bit of units. Why? Because we are trying to, or at least I am attempting to make the argument of the unreasonable effectiveness of SI, aka the metric system, which is a coherent system of units that, as far as I understand it, obeys these rules right here. Basically, F equals ma, force, equals mass times acceleration. Energy equals that force times a distance. And then power is that energy up there per unit of time. Once all these magical things combine, we have a coherent system of units, and you don't necessarily need to have constant factors as conversions there. Ultimately, especially once you have the modern SI system upon undergoing its redefinition in 2019, it is literally tuned to the constants of nature. So, as we can see over here, this way, we have our second meter, coulomb, Kelvin, and kilogram over there. Those are our reference ones of the system. And yeah, the second started off as basically an earthly convenience. Why? We can throw 60 of them in a second. It's like one Mississippi, 60 minutes in an hour, 24 hours in a day. It seems to keep track of the solar cycle pretty well. The meter, it's like 10,000 kilometers from the North Pole to the equator by way of Paris. And then the coulomb, I think that was defined as, something like 1 amp running through 2 copper wires, 1 meter. It seems completely arbitrary. However, once we set those bases, we have these referential rules over here. Yes, it's inverted a little bit. These referential rules over there, we can actually try to start parsing things and seeing what might be going on. And it's worked pretty dang well, because you go through, and let's just see, let's take some examples here. And we let folks roll in from wherever on the internet they may come from there. Or we're watching temporally in the future, because this is the internet, and we can do that type of stuff. All right. So let's go over here. Let's share with the class. Bada boom, bada bing. All right. We got a Wolfram Alpha. Okay, let's take a look at some things. So how about this? We got some constants. Let's take, the electric constant, and then we'll multiply by the magnetic constant, because those seem to go together like a horse and carriage. This I tell you, brother, you can't have one without the other. I'm sorry, that's terrible. Oh God, what am I putting you all through? All right, so you get what the heck do you get here? You get mass per energy. Oh my God, that's a big number. Since both of those are square, let's take the square root of it. Why? Because we can. All right, we get that. What is this? 10 times negative 9 seconds per meter. I have no idea what that's slowness. Well, what would the inverse of slowness be? Speed! Let's invert it. How do we invert it? We do the magic of putting 1 over it. We divide it into it, and bada boom, bada bing, we discovered what James Clerk Maxwell did 150 plus years ago. We've discovered the speed of light, my friends. All right, so that's just showing within our current coherent system of units, we can do very useful things. And then we should have the full 9 digits, because those are, I think we got about 9 to 10 digits in those. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, all 9 digits of the speed of light are accounted for. Groovy. Hey, welcome 6. Good to see you. Caught 2 streams in a row. Hey man, that's better than me. I miss some of my own streams a lot of the time. God, why? Professional YouTuber. And welcome log. Yes, another fun fiesta of learnage. Let's educate ourselves, shall we? Okay. This and ultimately this here. Okay. Yeah, there's an equation and everything. What is it? It's just stuff doing things. In this case, the benefits of the Wolfram language is you can just literally type just like normal natural language, like type the words rather than having to type in all these decimal places. It makes the situation for just doing it some, again, you can feel free to trust, but you also want to verify by going through and doing the actual numerical calculations and all that jazz and make sure like it at least kind of makes sense, because the whole reason why I'm kind of presenting this is to try to help bolster the arguments for things that I say, or at least are claiming, might make sense. And oh yes, we got all the fancy light refraction and everything here. Ooh, yes. Oh, look, the speed of light. And then we start having a little refraction through the window because I'm not doing it extremely late at night. Oh, look at all that cool stuff. But again, full disclosure, one of the reasons I'm making this argument is because if I'm actually going to finish writing that paper that I started and I never finished, at this point, I've got data that's within, I don't know, 4 mega electron volts. So the above unit is giga. So if we know from Final Fantasy VII, mega flare, giga flare, tera flare. Those are the 1,000 prefixes there. So that's 4 mega electron volts difference from the current, most recent measurement from CERN's CMS group that just won the Breakthrough Prize, and our prediction there. They have 125.38. We have 125.376. And that could swing up or down by 2. And that's constrained by the uncertainty that we have within the Planck mass calculation. Okay. Because all this literally is the Planck mass. And I don't go around saying this, but occasionally, well, okay, I do say it because I've made a video on it, but they have this thing called the hierarchy problem within particle physics. It's why is the Higgs mass so much smaller than the Planck mass? Okay. Because I think the argument of naturalness, and again, that's not necessarily a root of physics, but we would expect it to be of the Planck scale. Why is it 10 to the 17 times smaller? Basically, it's got like 17 zeros between, 17 decimal places between that thingy and that thingy. Why? Well, I claim it's scaled by the root of action. What is that? It's that little h bar, divide by that j, and then there's an s under there. It's kind of hard to see. So all that is the minimum of action divided by the reference one of action. So basically, like these units over here, these Planckian units, well, the unit of action is, we can do this, now, it's energy times time. So, well, how would we get that? Long story short, when you do it, it's a mass area rate. So it would be the Planck mass times Planck length. That's all squared divided by the Planck time. Okay. So all it is, it's a combination, and this should, I'm gonna say, approximately equals h bar. There's some caveats for personal reasons, but it's the Planck mass times the minimum area divided by the minimum unit of time. That's action. Why do I say it's energy divided by time? Because if you multiply by time, it goes into the numerator, which energy, that would be squared. So then we would have mass times a length, minimum of length squared divided by minimum of time. That's speed squared. So that's basically your E equals mc squared times a unit of time will give you a unit of action. Okay. So the claim is that thingy there is this thingy here, and then we have our reference dimensions. So this is the dimension of action. We would divide it by the dimension of action, which is energy times time. Standard unit of energy is that joule. We have defined up there times 1 second. And we just divide that out, and all that's going to do is it's going to make h bar, Planck's reduced constant, the elementary unit of action, the minimum one of action. It's going to turn it into a dimensionless number. And then since it's a dimensionless number at that point, we could just take the square root of that, We multiply the Planck mass, bada boom, bada bing, we're within 4,000ths of a giga-electron volt of the current measurement. I think that's pretty neat. Now, again, I'm laying this out, and okay, there's a whole bunch of stuff here. Let's actually get into more fun stuff here. Because, yeah, I'm saying some words, and yeah, who cares? People have big questions. It's like, what the heck is universe? How big is the universe? How old is the universe? How much stuff is there in the universe? Now, I'm not going to claim to have all these answers, but I'm going to show you a couple of real quick calculations that, to be fair, you can easily do on your own. And by doing your own, I mean you could type some words into Wolfram Alpha and then attempt to do digital wizardry to your friends and stuff. So let's do this. So erase the board. Hold on. So we had a Sky of Mind. The learning begins. Hello, welcome. So how about this? Let's conjecture. I'm going to commit some blasphemy because I'm going to have slight disagreement with how old the universe is. The benefit of that disagreement is I think it helps explain a lot of other things. And we're in the age where the quote-unquote impossible galaxies, how can there be so much stuff, like so far back and everything? And now it seems like a lot of the things that many people assume to be the case may not quite be the case. So you've heard folks saying, oh, it's panic at the Disc, and Eric Lerner is going, oh, they're panic. It's like, yeah, it's also a play of Panic at the Disco and stuff. And it was a bit of a hyperbolic expression, but at least things are fluid. Some folks may say there's chaos. If there's one thing I've learned from Game of Thrones, it's chaos is a ladder. And if that means that a lot of folks that may not have been previously open to some perhaps alternative interpretations to some stuff, seem to be becoming a little bit more open and everything to some different things. So any particular questions, comments, feel free to let me know in the chat. Let me know down below. I'm mostly just filling time while I'm erasing this because I know that seeing as my AirPods don't really pick up sound well, I need to actually talk towards the microphone and everything for it to come through. Actually, wait a sec. We have that other Bluetooth thing. I could just use that, derp. Okay. See? This is what happens. If I just go into a random stream of thought, I'm just going to keep on saying words and then often contradict myself because I realized I was incredibly wrong. Okay. So, I think we'll leave our little conversion thingy up here just because this is very useful. And also, if I make a grievous error, somebody can easily point it out because those happen all the time. As we saw with Fizz about a week or two ago, it's like, yes, a newly discovered moon from 150 years ago. I obviously did not pay attention to the subject that I was talking about. All right, let's do this. Do we want the funky sunlight or should I close the thing? I'm gonna keep it here for the moment being. Where are we? Well, Sky, that's a very good question because what was it? Standard interpretation universe. Basically, if we were relying general relativity, as far as we know, we get about 14-ish billion years. Okay. And then Professor Gupta from the University of Toronto, he had actually said something where he had done a paper. He was accounting for some variable like speed of light and changing constants and stuff. And one of the reasons he did that is to help give some more time for the generation of galaxies and stuff, because we're finding all these old galaxies that seem to be bigger than the Milky Way, and again, not all, but some. Yeah, that's kind of hard to explain with our standard galaxy formation models and stuff. So, and that ended up being about 28 billion years. Okay. I'm going to give a number that's a wee bit larger. So, well, this is the thing. Oh, well, 6, you know probably better than a lot of people. Questions can also be very dangerous. So, okay, so what happens if we take things seriously? All right, okay, I think. All right, as long as the board isn't obstructed by the light, which it probably will in a few minutes, we'll adjust it then. Okay. So there's this very interesting thing called maximum extendability. Okay. What does that mean? That's, at least to my knowledge, a framework of logic that we're using to figure out what's going on. Okay. Basically, the claim is if you have a minimum of something, the logical extension of that would be, what would the inverse of that be? Well, the inverse of that would be a maximum. Okay. So, to my knowledge, again, I'm not a professionally trained physicist. I don't have a PhD in physics. I'm a dude on the internet that's very interested, like a lot of y'all and everything, and had to have a lot of questions, and somehow became a monk at the Physics Monastery. Okay. Ultimately, a lot of folks, one of the things that you have kind of like with quantum gravity and stuff like that, it's like, all right, we can get down to like the Planck length, and then we don't know what to do after that. Now, that seems to be inferring that we can continue to go down indefinitely. Like, there is no minimum. We can just keep on going, blah, 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 blah. Even though when we do a calculation, we get, well, I just erased the Planck length. There does seem to be a minimum of length, okay, to our known physics. Now, might there be stuff below that? Perhaps. But the thing is, if you have to keep on going down smaller and smaller and smaller, if we were to follow maximum extendability, if things can get infinitely small, well, the inverse of that must mean that things get infinitely big. So if universe, whatever that is, goes on forever, that's pretty hard to conceptualize. And there seem to be a number of folks that believe that. It believes, okay, we're going to continue outward forever. All right. So I'm going to claim that what if we just took like the physics that we know for the most part, if we have a minimum of length, what would happen if we extended it to its maximum? Okay. So what would that mean? So let's just do the little thing here. We'll show the little bit of magic. All right, as we go back to our friend Wolfram Alpha. Okay. So we've got this thing here that's called the Planck length. Literally just type the word, you hit enter, and then, oh God, the lag is real. The lag is real. Must be ChatGPT and all those LLMs, which seem to be one of the big customers nowadays. Oh my God. This is atrocious. I might have to go back and add some of these things and let's reload this. Hold on. Let me give myself a new window. Ooh. That's okay. Here we go. Oh yeah, it's definitely lagging on. There we go. All right, back after these messages. We'll be right back. Ooh, some tea sounds pretty good. I might make myself a hot chocolate. All right, we got the Planck length here. What is this? Stuff behind is this. It's the square root of the Newtonian gravitational constant, h bar, the minimum unit of action, divide by speed of light to the third power. Okay, it gives you this. What is this? 1.6 times 10 to the minus 35 meters. Redonkulously small. So like an atom is like, I don't know, 10 to the minus 10-ish meters or so. So it's like 25 magnitudes or decimal places difference between the size of an atom. Frickin' small. So hypothetically, how would we extend this? Well, you do that 1 over thing, okay. Gives you this, but we're in the wrong units. All right, you want to see a little trick? Watch this. Since we've gone over our coherent system of units, the Planck length is expressed in meters. So what happens if we divide it into meters? Well, we've got a dimension of length divided by another dimension of length. It gives us a dimensionless number. But we don't want a dimensionless number. We want a dimension-full number. All right, what do we got to do? Well, since this is 1, we square it. Since we know 1 squared is 1, the 1 shall remain, but there's an additional dimension there because we've gone from basically a length to a square area. Okay. But since we're dividing it by a length, we're going to get our same dimensionless number out within the dimension that we're looking for. All right. What is this? 6.1 times 10 to the 34 meters. An absolutely ginormous number. How ginormous is it? Well, it's right about 100 million times larger than the diameter of the observable universe. Okay. Now that's a giant number. Oh, and quickly, so how long would it take for hypothetically, and again, I'm going to show some more calculation. You know what? Let's hold this. Let's hold off on this because this is going to be a fun thing. So let's throw this on the board. So we'll get some numbers here. All right. Well, to be fair, it's. I mean, the AI does work, and I think that's actually what's prioritizing a lot of the calls on their network there, because even Stephen Wolfram was like, yeah, basically one of our top-rated things now, like one of our greatest new user bases are LLM agents making queries and stuff. So let's throw this on the board. Okay, so let's claim, oh God, okay, I'm going to put, again in quotes, lower U universe, because it seems like a weird thing. Universe. Okay, so let's do min and then max. Okay, now well, I'm going to change this to limit. All right, let's see how this goes. Because as I'm writing this, I'm realizing this might not be completely true. Okay, so we're going to do, and then length. Okay, so we'll move this over. So we'll do a min max. There we go. And dimension. Dimension. Okay. It's going to be dimensions of measure. So ultimately, if we had precise enough equipment, we should actually be able to do some measurements of these. Oh, actually, to be fair, that's a lie, because if we try to measure the Planck length, we would technically create a black hole. Okay, so I lied. Oops. Okay, so we're going to do a dimension of length. So we're going to claim the minimum is Planck length. That's L sub p. And that's about 10 to the minus 35 meters. Okay? So and then the max, we're going to say is meters squared. So m squared. Well, let's actually write it out. Because otherwise, I also use m for mass, so meters squared over LP. So that's going to give us about 10 to the 34 meters. Okay. So again, we're following a claim. Now again, that claim could be completely wrong. I'm realizing I'm going to have to close this because otherwise it's going to block everything else. All right, sorry. Into the shadow realm. There we go. All right. Freshen up my root beer. Why? Because we can. Exactly. Hydration. Hydration is also good. All right. The Mandelbrot set is fascinating. All I know is depending on how you want to break up things and look at them, you can get a much different perspective. Listen, if the Mandelbrot set is something within our reality, well, you know what, then it's within our reality. Now, the extent of which it sufficiently may resemble our reality, well, I know Fractal Woman's talked about that before, so She's really big on that. I can't say. I know Thad has talked about that a little bit, and there's some very interesting things here. And let's just say the whole quote-unquote complex plane and stuff is something worth exploring. So let's continue here. So if we've got that, okay, so we've got a dimension of length. Well, what can we do with that? Oh, you can start to do the different derivatives and stuff like that. So it's like, if you got a length, when I say derivative, I just mean square that dang thing. So you get an area, and you'll get a volume, yada, yada, yada. And then if you want to model it after a hypersphere, you just put like a 2 pi squared or something in front of it. Again, don't quote me on that. But the question is there a bottom level? I think time might be a limit there. So whether you want to look at time or its inverse frequency, that just may be a matter of perspective. I don't have an answer. I can make some claims and stuff. I can't get something from nothing. We're going to go back. We still have enough time. Coincidentally enough, that we should be able to go through a few other things. So let's go to, we did a dimension of length. So, oh, God, I'm realizing, let's go to mass. I'm gonna skip ahead for a second. Why? Because I actually have a pretty, at least conjectured explanation, or at least calculation for this. All right. Oh God, I realize I don't necessarily know if there is a minimum for mass. Okay, we're gonna do unknown, because I actually don't have an answer. You could say it's the minimum neutrino, because it's the lowest masses we know about. However, if you did have the ability to actually convert an extremely weak photon into mass, I don't know if that's possible or not. So, all right, I don't know. Unknown. Okay. So, the maximum mass, okay, to be fair, is actually the Planck mass. So this is where I need to erase those things, because it doesn't make any sense anymore. Okay. So, all right. Here we go. All right. See, this is why we do it, because we need to follow logic. Our logic needs to be coherent, so we're going to say base and limit. All right, here we go. Base, limit. Okay, see, I might even change these around more, because a lot of this is actually just practicing, because I've done some of these calculations before, but I didn't necessarily say it in the same way, because you could say something one way and you say something another, but you want to be saying the same thing. And yeah, you can do a calculation, but if you're using different words and people don't really understand what you're saying because you're using different words, you want to use the minimal necessary description with maximum explanatory power. I know Tyler Goldstein has hit upon that names are very important. I agree with him on that. So let's change this. All right. So now that we're doing it in bases, we can actually write it out like this. So base, it's actually do m sub p. So m sub p is the Planck mass, and that's about 10 to the minus 8 kg. Okay. So how the heck are we going to do that? Now, could we try inverting that? I did. We get about the mass of a supertanker. There's a lot more than a supertanker's worth of mass within the universe than we can see. So it's like, what's some logical way where we could try to figure this out? Okay. So if we've done something like this, all right, we got meter squared over length. Okay. And we saw we could do a dimensional thing. divided by another dimensional thing, we'll get a dimensionless number. So let's just act completely haphazardly here. And let's say, well, okay, let's do something here. Let's do like, I don't know, meters over the Planck length. That's gonna give us a really big number. Let's do something kind of crazy. Let's throw our protective brackets on, because it's better to have them and not need them than need them and not have them. And let's just move that exponent to the outside. Boom. That's gonna give us a really ginormous number, like 10 to the 69 or something like that. Yes. That's actually what it comes out to be. All right, and let's do a very simple equation, like literally middle school, maybe some high school algebra. All right. Yes. Don't worry, we don't actually have to do the algebra. Wolfram Alpha does it for us. All right, so let's take this whole thing. Let's set it equal to something. All right. So we got a dimensionful thing divided by a Planck thing. So let's do this. We got dimension of length. Let's put a dimension of mass in the denominator. M sub p. That's the Planck mass. And we'll divide it by, well, we're trying to solve for something, so we'll solve for x. And since we want it to work, this is in the dimensions of mass. So let's solve for the dimension of mass, which is the kilogram. So I just write kg over there. And we solve for x. So, all right. Let's get weird. All right, so all we're gonna do is we're gonna take our previous thingy that we had here, throw our protective brackets on, we're gonna square it, and we get our 3.8 times 10 to the 69. Now all we're gonna do is solve for x, kg, kilograms, divided by the Planck mass, and we set that expression equal, and we say, go, Wolfram Alpha. Well, now it does the maths for us. Gives us the stuff, gives us these things. What the? Oh my God, that's a lot of numbers. That looks like a little bit more, because remember, we're solving in kilograms. That looks a little bit larger than a supertanker. How big is this thing? Oh God, it actually has a factorization in there. I was not okay, and remember, it only has so much data there, so it's just arbitrarily filling in numbers. So we have accuracy to about 5 digits. So hold on, how big is this? All right, 8.3315 times 10 to the 61. All right, so let's click on that. That's how many kilograms we got. All right, so let's take off all those extra digits outside the known digits. All right. That's why we can't have nice things. All right. Times 10 to the 61. And we solved for the unit of kilograms. So let's see how big that is. All right. So this is our number there when we solved for x in our previous expression. So what's that? Oh, it's about 100 million times the mass of the ordinary matter in universe. Huh. Wait a second, when we did that length calculation, the radius was about 100 million times larger than the observable universe. This 10 to the 8 is because, remember, thousandths is 10 to the 3, millionths is 10 to the 6, billionths would be 10 to the 9, since we're 10 to the 8, that's less than a billion, so that's like 100 million. All right. So, okay, well, this calculation seems to match the 100 million magnitude larger than our observable universe. Oh, very interesting. And this would be the E equals mc squared thingy. That would be the amount of energy in joules. We're going to come back to that. Actually, I think we're going to go to that next because, to be fair, this is about as far as I've actually gotten with this. We could go through some more things, but let's just say my confidence goes from This is very interesting speculation that seems to line up to. I got a grasp for straws. Okay, I apologize. I only got through a couple of dimensions. You know what? No, let's do time. Let's do time. We'll do that because that'll bother a lot more people. So all right. So the claim is. Let me finish this guy here. So the limit over here would be this thingy expression. Draw some lines so I don't get confused because I'm already getting confused. So this expression would be x kilograms divided by the Planck mass. Is that equal to meters over the Planck length? And then this expression is squared. So, all right, we're setting a length. A square of a length can help get us something to do with a kilogram? Well, it's not like it's already like E equals MC squared or something like that. But we have time in there. Okay. I haven't gone that far yet. Let's go to some of there now. All right, and this is about 10 to the 69 kilograms. All right, let me grab the other markers because this is. So I'm not holding up quite as well as we'd like. So let's go. All right, so let's go to time. Time, I know we skipped ahead. Oh, very fitting. Time, the base, the minimum of time is the Planck time, T sub P, and that's about 10 to the minus 44 seconds. Redonkulously small. Okay, it's the greatest magnitude of these different bases. So if you're looking for a bottom turtle, so to speak, sky, time might be your answer. It's conjecture there. Again, people can feel free to disagree. All right. So time. We're going to do a quick calculation. Because this is the part where my ontological basis, or how I go about conceptualizing things, breaks with a lot of other folks. Number one, I don't know. Hey, Nolan. Good to see you, my friend. This comes packaged within seconds. Well, see, that's the interesting thing. It's kind of like a combo plate. It's like it kind of just comes with it and stuff. It's like, listen, you get your Kung Pao chicken, your General Gao chicken, you get your noodles, you get your broccoli, bada boom, bada bing, you got your 3-item combo. All right. So let's see. More universe than universe. I think Rob Zombie would be proud about that. Can't say. So, all right. So let's do a quick calculation for time. I do need to actually use Wolfram Alpha because otherwise I think I'm going to get lost. Okay. So, let's see. All right. We're starting from about the magnitude of an electron. Oh, let me show you something cool. Why is this number? Okay. I just solved for x divided by the Planck mass, and I'm claiming that number is equivalent to the, let's say, mass energy bank of universe, or at least the mass bank, so to speak, because if there's a conversion, maybe it's energy, maybe it's mass. And here's also where I start to run into some problems. It's going to depend on measurements and our interpretation of the cosmological constant. So the whole claim is, I literally just I'm like, all right, let's take meters, divide by the Planck length. So the reference one divided by the minimum one, we square that, and then I'm taking the base of mass, the base one of mass, divided by the reference of mass, the kilogram, and we're solving for x, and then we get this ginormous number we have here. How the heck could I justify this number? Okay, so there's this interesting thing that one of the benefits of Wolfram Alpha, if you just play around, all of a sudden you learn things you never, and again, had I had a full formal physics training background, I probably know these things. So there's an interesting thing that happens if you have a mass over seconds squared. There's a particular dimension that, oh wow, that's so laggy. Go, Wolf, reload. All right. So, well, that is slowly not working. Let's skip to the punchline. Let's just take our Planckian unit. So, Planck mass divided by the Planck time squared. Okay. It gives you a ginormous number. It gives you 7.488 times 10 to the 78 kilograms divided by seconds squared. What the heck is that? Interpretations. Spring constant. That would mean if we're forming it with Planckian units, this is the Planck spring constant. Oh, that doesn't have something to do with that harmonic oscillator or like that basic equation that helps you figure out a lot of the force stuff in physics? Oh, very interesting. And again, there's more interpretations. Spring constant, a force gradient, linear force density, stiffness, surface tension, tear straight, peel straight, cleavage. All right. We're going to go with spring constant because a spring, a wonderful thing. Everybody loves a slinky. Okay. Wait a second. Spring constant. Why does this number look so familiar? 7.488 times 10 to the 78. Well, my friends, let's take our mass and convert it to energy now, shall we? What happens? Huh. That seems odd. 7.488 times 10 to the 78. Now, the dimensions are not the same. We must note that. But wait, hold on. So, according to that calculation, the mass energy of the universe from that calculation is of the same magnitude as the Planck spring constant. That's weird. What is the difference? It's the same magnitude, but there's a dimension because we got kilograms and we got seconds divided by seconds over there. We got kilograms and meters. So, let's literally take this. We copy. We paste. And we divide the whole dang thing. And let's see what our common factor is. This is the exact moment the internet lagged out. Yeah, we'll reload as I hydrate. There we go. What do we got? Oh, look! 1 meter squared. That's interesting. We get a reference 1 squared. Well, I mean, why is this the case? I don't know. All I know is I play around with some of these calculations, and a lot of time, the common factor comes out to be 1 meter squared. I don't know why. I'm sure it's just a matter of our convention within our coherent system of units. I also just haven't seen other stuff out there with people talking about these particular magnitudes or constructions that seem to have pretty strong agreement for many of them that basically magnitude, if we assume maximum extendability, universe, it's about 100 million times larger than what we current the observable universe. Now that's freaking ginormous. It's not infinity. Because as long as it's less than infinity, we can at least try to conceptualize it. It's kind of like, I love the William Blake quote. It's like, to see a world in a grain of sand and heaven in a wild flower, hold infinity in the palm of your hand and eternity in an hour. It's from Ultraman Towards the Future. That's when I first heard that. But all right, so where were we? Oh yeah, I was supposed to be talking about time, and here I am talking about everything else. Oh look, this mass energy happens to line up pretty dang well. All right, that's a neat little trick. So, all right, so time. All right, I'm not gonna subtract out the magnitude of the radius of an electron. You have to grant me that I'm going to be off by about the magnitude of an electron. Okay, for our time calculation, because you can plug in inflation if you want or something like that. For me, I'm very boring because, oh yeah, I forgot to show you. So the other interesting thing is if we take this mass here, oh god, I should actually share it, derp. Let's take this. If we have this full mass here, let's divide it by something. But before we get there, let's check out another Planckian thing. Let's do the Planck density. Okay, so we've got rho sub p. It's that funky looking p there. That's rho. It's this definition. Speed of light to the fifth divided by Newtonian gravitational constant squared times Planck's reduced constant. Okay, so 10 to the 96 kilograms divided by cubic meters. That's a mass density, my friends. That is frickin' dense as all heck. Why? Well, because it's going to be the Planck mass divided by the Planck length cubed. Why? Because it's Planck mass divided by the Planck length cubed. Because that's what it is. Because it's a base of mass, the Planck unit of mass divided by the Planck unit of length. Okay, ginormous number. I saw this number. I had no idea how to make sense of this. It's like, okay, yeah, I understand that comes out. What significance does it have? Because it's like, normally it's like, you look at the total mass of our observable universe, it's like, I don't know, like 10 to the 50-ish, something like that. Like kilograms, it's like, where the heck does this come from? All right. So let's just take this and let's literally just divide it into this because we can. All right, so we've got estimated limit of mass for our mass bank of universe divided by the maximum density of nature. What do we get? Well, that's weird. This number looks incredibly familiar. But it's, wait a second. That looks suspiciously like the Planck length. 1.6 times 10 to the minus 35 meters. 1.6 times 10 to the minus 35 meters. Okay, so, all right, we got 5 digits there, so it's giving us 4 digits of accuracy, so we got the Planck mass, but it's in the wrong unit. It's in cubic meters rather than just meters. Now again, maybe this shouldn't be surprising given our construction there, because we're literally just squaring that dang thing, but I find it interesting that if we do that calculation, we get the Planck length in meters squared. Meter squared strikes again! Yes, in this case, this is one of the few instances within dimensionality that 1 times 1 does not necessarily equal the same 1. It's the 1, but your dimensional powers have changed. Okay, so we've got that number there. All right, that's neat. Okay, but this is a volume. I don't know how much volume that is. That's ridiculously small. It's giving us... Let's take a look. So since that's a volume, we can do the magic of maths. And if it was a square thing, we would take the square root, which if we put in the little exponent thingy here, the square root would be 1/2. But we've got 3 dimensions of length, so we raise it to the 1/3. See? Because we can. So what do we got? We got 10 to the minus 12 meters. So about how big is this? So if we were to take the maximum mass bank, so to speak, of universe, and we were to crunch it down into the maximum density, about how small would it be? Well, roughly about the Compton wavelength of an electron. So if we take from that calculation and we were to crush it down all the way to the maximum state of density, we conspicuously get something that looks kind of like the radius of the electron. I think that's the Bohr radius. So that eerily sounds very akin to a quote-unquote primordial atom if we were to go back there. Okay. That was a very long-winded way to get to the actual point. Okay. Because once we actually have this point, okay, that's interesting. So technically, how long would it take for, let's say, us to get to that maximum extent? Okay. So, okay, I need to remember how the heck I do this again. What is it? We need to go for C divided by... Hold on. Wait. We're going to rampantly conjecture here. Hold on. I need Wolfram to cover my butt. Here we go. Let's...
Although this is going to be weird, and it's going to be about a different...
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
All right. Oops. Sorry. I'm cheating. I'm looking for where it is. All right. Oh, God. All the numerology. Primordial. Okay, I think it was this guy. All right. Hold on. All right. So we're going... Oh, that's the other thing. Hold on. There's one more calculation we can play with this. All right. Hypothetically, if you took this and you were to just, with reckless abandon, divide it by another number that you use within science and physics and a lot of times chemistry. About Avogadro's number. What the heck is Avogadro's number, you might ask? All right. Avogadro is... Avogadro. Oh my God, I'm spelling everything wrong. It's okay, correct. All right. It's that ginormous number there, that 10 to the 23 thing that they taught us in chemistry in high school. It's the amount of approximate atoms or particles that would be within a mole, so to speak. Okay. So if we take Avogadro's number and we just haphazardly divide it into that massive, quote, universe calculation, what do we get? I get 1.3 times 10 to the 38 kilograms. 10 to the 38 kilograms. I don't know what that is. Don't worry. You don't have to know because Wolfram Alpha knows. What's that approximate mass? 10 to the 38 happens to be the mass of a typical globular cluster. Globular clusters, aren't those star-like birthplaces where all of a sudden globular clusters come together and start making galaxies? What a coincidence. I know I haven't even gotten to... Oh, God, I didn't even have my calculations in this one. This is terrible. Where do we get to? Did I even do the calculation here? How do we do this? Okay, let's just do this. Let's take our... Here I am trying to conjecture about things that I don't even know. Of all the things that I've learned, I've forgotten the most. Let's see. Reload, laggy. All right, here we go. So let's take our radii here. Oh, wait, I could have just done that from... All right. Let's do this, times that, and then... So if we were to assume non-inflation, and again, just conjecturing here, we played our Wolfram thing, we're conjecturing ahead. How long would it take to get that maximum length? Okay. Oh, yeah. And you divide by c squared. It said we'll cancel out the length, and then we'll get something within time. All right. So that would take approximately, what is this? 10 to the 26 seconds. All right. So if we used a Gregorian year, aka our standard year thingy, all right. So that's 10 to the 18. All right. So let's just do this. Let's divide it by the age of universe, as far as we know. Okay. 470 million. That coincidentally seems to be around within the same magnitude of that 100 million magnitude greater calculation we had. Oh, very interesting. So what are we saying? Well, it sounds like if we were to take it to the maximum, and that is the time, might that just be the time of universe? Maybe it is. Maybe it is. 470 million times longer? Maybe. I'm gonna break a bit of a cycle, because that is how long it would take if we started from zero. Again, grant me the radius of an electron if you would. And it would take about 470 million times longer than the current accepted age of the universe by most folks in order to reach that maximum extent. Now, are we at that maximum extent now? I don't know. It's hard to say because it depends upon your interpretation of the vacuum energy. If you want to say the vacuum energy, if dark energy or whatever the heck that is remains constant, okay, then if that's built in as a field configuration, if it's a factor of how much of this stuff is within here and it is weakening over time, then we could actually just plug in that mass energy scale and we might actually be able to explain a lot of things. Now, again, I don't have an answer. I have different paths and there's a lot more work that we need to do. So ultimately, let's go back to our board here. Okay. So time, limit. This is an ontological claim. I'm going to claim it's a lemniscate, aka infinity. Because if we take the model that Thad had put forward, and we were to interpret it as if it was actually balanced, if we are actually the inversion of the minimal double cover manifold, the hyperbolic figure 8 knots complement that projects a toroid. So basically you get a torus, and one of the things we learned from John Williamson, God rest his soul, as well as some of the other literature out there, that the inversion of a torus is a hypersphere. So if we happen to live in the n hypersphere maximal volume, well, if we happen to have a four-dimensional sphere, you have four-dimensional content. Well, they say we live in 4 dimensions, or 3 plus 1, and for some reason, if we do it within 4 dimensions, we can kind of weave it together with time and everything. And then why would our space be present within 3 dimensions? Well, to be fair, 3 dimensions is the only dimension where knots make actually sense. Because otherwise you go to 1 dimension and you just have a line. Well, if you got 2 dimensions, even if you're trying to do this, you're saying there's a crossing there, but does it actually cross? Because there's no height. You need to at least have a volume, at least have some cubical thing for some form of a knot to make sense in. You actually need it to have it cross. Once you get to 4 dimensions, things can just wiggle all around kind of haphazardly. So that's the thing. Knots can only be tied in 3 dimensions. That's probably the strongest argument I have right now for that. And I realize I didn't actually get to that and didn't really even explain why that infinity would be the case. It ultimately comes down to the ontological conjecture that if we happen to live in something that may not necessarily be infinite in length or size, but it may be balanced by infinite in time. Now that could just be a whole bunch of hooey. Maybe there's going to be a crunch, going to be this, going to be that. But that's an interesting thing. And to be fair, let's rewrite this. To get to max radius. So to maximal extension would be whatever that crazy number was, 10 to the 26 seconds, or let's do that in years. All right, so 10 to the 18 years. So that would be 10 to the 18 years. Yes, I know. I'm abandoning metric system just for human thoughts there. So again, if we take a real quick look, it's like, all right. So we've got dimensions of length, mass, and time. We've got our bases. We've got really small, pretty dang small, redonkulously small. Okay. And then when we take the limits, we're going to say that this is big. So each one of these compared to our observable universe, it's 10 to the 34. It's about 8 orders of magnitude, or 100 million times larger than the observable universe, as we know it. This mass here, this 10 to the 61 kilograms. Because this is a 69 and that's -8, so it ends up being 10 to the 61. Apologize. All right, so that's about 8 orders of magnitude, or 100 million times larger than the mass of the observable universe. And then this time thing, again, personally, I'm willing to conjecture that our realm may just persist. At that point, it actually does solve, I think, a lot of problems. But at the same time, if we were to start from that primordial atom, so to speak, that about the size of an electron in volume, the time it would take to get to the maximum extendable radius and size is about 100 million times longer than the current estimated age of universe. So we seem to have a lot of 10 to the 8 factors larger. So ultimately the claim is many of the factors within universe, or our realm of persistence, seem to be right within about 100 million times the magnitude. So again, that's freaking absolutely ginormous, because our radius are 10 to the 26 meters. It's like, if it's like 10,000 kilometers from the North Pole to the equator, it's like that's 10,000 kilometers. Guess what that is? That's 10 to the 4. You got 22 more zeros onto that, and you have basically the radius of our observable universe. All right. Now go 100 million times past that, and that would be approximately radius, or the maximal radius conjectured within this claim of universe. I think that's enough. I realize, but all it is what do? We just took some things, we did 1 over it, we just canceled out some dimensions. So that's why I said this is what we might be able to glean. And again, I'm not saying this is right, but if we proceed with reckless abandon, might we find interesting things? Because I'm willing to claim that any sufficiently crazy idea is indistinguishable from madness. Yes, I totally ripped off Arthur C. Clarke there, but I kind of feel it's true. Because you've had folks, it's like, it's not like Galileo or some other folks there that, Copernicus or whoever it was, that literally waited until their deathbed to hand it to somebody to publish because they were so afraid of being criticized. It's not like the internet's made that worse or anything, but there we go. It's, what is a cubic meter? Well, it might be the volume of 1,000 kilograms of water, or at least within a particular pinch of salt addition. Well, Sky, here's the thing. I don't talk about that. You're talking about the meter squared, a potential holographic thing. Here's the thing. when I said that four-dimensional hypersphere, here's the thing. Okay, let's just go right to it because it's right here. All right, so present. And we get this window, boom, boom, okay. So if we have the little calculation of the thingy here, let's reload. Okay, I covered the volume, which is four-dimensional, because they'll give you all these things. Yep, there's our 3.8 times 10 to the 69. That's basically just the inverse of the Planck length squared. Okay, so it gives you a four-dimensional content. So the delicious four-dimensional center is expressed in this. However, if you look at this, that hypersurface area is basically the surface is in 3 dimensions. So what does that mean? You may have noticed there, if I'm going to make the claim that the content, this four-dimensional, four-volume content, is actually 3 plus 1 dimensions. So 3 dimensions of space, 1 dimension of time. I'm going to need to follow the same logic and say that, well, that 10 to the 105 cubic meters, that's actually 2 dimensions of space and 1 dimension of time. What might that mean? Are we at the interface of the frequency being generated by different surfaces? Maybe. But that's one of the interesting things. And to be fair, if you wanted to attach some form of holography there, again, this is in 4 dimensions. It's a 4-dimensional hypersphere expressed in 4 dimensions. And again, I'm saying if there are 5 bases or dimensional things there, again, maybe you want to convert them back and forth, but okay, now I'm just speculating out of my butt now. I realize I do that a lot, but it's just something to ponder over. All right. Hey, I'm a Taurus too. Happy B-Day, my friend. Yeah. All right. So it depends on, well, Nolan will save volume creation and annihilation for another day. That's the synchronicity of the universe is amazing. So that's basically what I got. So, all right. Well, with that, take care of yourselves, everyone. Peace out. It's a crazy world out there, but